Hi people, I hope we're doing well today. Now for a couple of videos on we basically spent a little bit of time just dealing with the algebra of partial fractions, and like I said in class, that's because in the past I actually had calculus students who had been exposed to it already in Algebra 2 and Pre-Cal, and so I wanted just to spend some time on just the algebra because it's complicated enough, and then fold it in to the integration because sometimes there's a couple extra steps even after the decomposition into partial fractions in order to get into a form that is integrable. But we're going to go ahead and start, and I've done my best to try to put these in ascending order according to difficulty. And so we'll start off pretty easy. I mean, this one should be relatively straightforward. It has two linears, so we're going to be able to use the Heaviside method and basically use those convenient values to find our numerators rather quickly. Now, what we have here is we have x plus 4 and x minus 1, and I know that when I pull that apart, it's going to be into a, x plus 4, and b, x minus 1. As we have been doing the whole time, we're going to go ahead and multiply through by the denominator, and this winds up being something like this. Now, we can solve for a and b by plugging in any old number for x, right? Because this is true for all x, if I plug in just random values of x, I will get a system of equations in terms of a and b. But because there are particular values that make each of these expressions equal to 0, I'm going to go ahead and let x is equal to 1, and that makes x minus 1 0, but that makes x plus 4 5. That goes bye-bye. That was kind of the point. And I'm left with b is equal to 1/5. Now I'm going to turn around and do it for the other expression, let x is equal to negative 4, because when x is equal to negative 4, x plus 4 is 0. And I'm left with, this becomes negative 5 plus b times 0. That cancels out. Again, that was kind of the point. And I'm left with a is equal to negative 1/5 and b is equal to 1/5. Well, I don't like fractions in the numerator, so I'm going to go ahead and factor out that 1/5, and I'm just going to be left with negative 1 over x plus 4 and 1 over x minus 1. But let's go ahead and turn that around, simply because I don't want to deal with the negative. I'd rather deal with a minus sign. And this winds up being our decomp. Now, because this expression is equivalent to this expression, I can go ahead and just plop it into my integrand, and I'm going to get 1/5, 1 over x minus 1 minus 1 over x plus 4. And, you can split these up into two separate integrals if you want, but it's pretty easy term by term. So it's, if you were to split it up into two separate integrals, it would simply look like this. And having done that, we recognize that it's 1/5 natural log absolute value x minus 1 minus 1/5 natural log absolute value x plus 4 plus c. Okay. And that didn't wind up being too burdensome or too difficult. Okay, let's go ahead and let's do another one. This one also will have simple linears in the denominator. And so we're going to do the decomp with 3x in the numerator and x plus 2 and x minus 4. That's going to be a over x plus 2 and b over x minus 4. Again, multiplying through by the denominator, so we're turning it into a polynomial rather than a rational structured equation. And we wind up with this. Again, because we have simple linears and we can plug in convenient values in order to make those expressions, being x minus 4 and x plus 2, equal to 0, we're going to go ahead and let x is equal to 4 to isolate b, and we're going to let x equal to negative 2 to isolate a. So let's x is equal to 4. 3x becomes 12. This becomes 0, so I'm just not even going to put it. And b, 4 plus 2 is 6. And when I have negative 2, this becomes negative 6 over here. X plus 2 becomes 0, so I'm just going to ignore it. And a times negative 6. So b is equal to 2, and a is equal to 1. This winds up 1x plus 2 plus 2x minus 4. And in your mind's eye, you can even sort of think about what it would be like to push them back together, to get a common denominator and push them back together. When you multiply this one over here by x plus 2 over x plus 2, you're going to get 2x plus 4. When you multiply this one by x minus 4 over x minus 4, you're going to get x minus 4. Well, the minus 4 and the plus 4 are going to cancel. The x and the 2x are going to combine to give you 3x. Now that I have it like this, I recognize that the original integral can be rewritten simply as 1 over x plus 2 over x minus 4 dx. And you don't have to, but just like we did in the last one, if you wanted to rewrite it such that you could actually see the independent integrals, that's actually minus 4, there we go, then basically you would do this. So natural log of absolute value of x plus 2 natural log x minus 4 plus c, and there we go. That winds up being our integral after we've taken that apart into partial fractions. Now, let's go ahead and make it just a little more difficult, and we're going to have still linear factors in the denominator, but one of them is going to be repeated. And that means that I can rely on the Heaviside method to get most of my values, but there's going to be a little bit of work after that in order to get the rest. Now remember, when I have a repeated, I have to put a over that and then actually step down 1 degree and put b over that first degree, and then c over x minus 2. Multiply through by the common denominator, and a winds up being times x minus 2. B winds up being times x and x minus 2, and c winds up being times x squared. Now let's use the only two values that we can actually, the two convenient values that we can use. So let x is equal to 0. On the left hand side, that's 0 plus 1, and we get a times negative 2, and then these other two are going to be 0, right? Because that factor is going to be 0, and that factor is going to be 0. So it just winds up being a is equal to negative 1/2. Now, let's let x is equal to 2. If that's the case, the left-hand side is 2 plus 1, or 3. This term is going to be 0 because x minus 2 here is going to be 0. This term is going to be 0 because x minus 2 here is going to be 0. And I'm left with c times 2 squared, or c is equal to 3/4. Now, when we plug that back in, we're going to get x plus 1 is equal to negative 1/2 x minus 2 plus bx x minus 2 plus 3/4 x squared. Now, you need to be able to work with fractions, but as I've always said, if you don't have to, why would you want to? So let's go ahead and multiply this bad boy through by 4, and we're going to get 4x plus 4 is equal to negative 2 x minus 2 plus 4bx x minus 2 plus 3x squared. Let's go ahead and expand all this out and see what we get. We're going to get negative 2x plus 4 plus 4bx squared minus 8bx plus 3x squared. Let's go ahead and reorder that and combine like terms. The x squareds, I have two of them. I have 4b plus 3x squared. I have a negative 8b and a negative 2 as coefficients of x. So I guess this actually should be negative. and we'll call it, actually let's go ahead and make it positive and put the negative inside, x, and then plus 4. Well, that's equal to 0x squared plus 4x plus 4. Now remember, I can compare these coefficients because this is true for all x, right? It's true for all x, and therefore when I'm not trying to find x, I'm trying to find b. So let's just go ahead and set the coefficients of the x squared equal to each other. So that'd be 4b plus 3 is equal to 0, and b is equal to negative 3/4. So I have a, I have b, I have c. It's going to be easier if I go ahead and factor out a 1/4, and that's going to leave me with negative 2 over x squared, plus a negative 3 over x, plus, that's a negative 3, plus a positive 3 over x minus 2. This is our decomp. This is equivalent to this integrand, and therefore we can set up the integral with that in mind. So let's go ahead and do that. We're going to need another sheet of paper because I'm writing kind of big. So what we have here is we have 1/4 integral of negative 2 over x squared plus negative 3 over x plus 3 over x minus 2 dx. Okay, well let's continue working with it on this sheet. And of course, let's just pull it into its separate integrals, and we get x minus 2 dx minus 3/4 the integral of dx over x plus 3/4 the integral of dx over x minus 2. Now, the integral of x to the negative 2 is negative x to the negative 1, so the negative of that integral will cancel out with the negative of the coefficient that's sitting out in front, and you're going to get 1/2 times 1 over x, or 1 over 2x. This one should be relatively straightforward. It's just natural log with the absolute value of x. This one also should be straightforward. It's simply the natural log of the absolute value of x minus 2, and then I tack on a plus c. Okay, and you're thinking to yourself, I don't know, did we do that correctly? Well, let's see. If we basically want to check, I know that this, I basically simply need to take the derivative of the answer. So let's basically take the integral and let's set it up. I'm not going to put the plus c because I know that the moment that I take the derivative, that derivative of a constant goes away. So you get y prime is equal to negative 1/2 x to the negative 2. I get negative 3/4 times 1 over x. I get positive 3/4 times 1 over x minus 2. This is negative 1 over 2x minus 3 over 4x plus 3 over 4x minus 2. Now, if I wanted to then check whether I can get it back into the form of the integrand, I would basically get a common denominator, right? And so I need a 2, an x, another 2, and an x minus 2. So in order to get a common denominator, this one needs another 2 and an x minus 2, 2 and an x minus 2. This one has the 4 and the x. It simply needs the x minus 2 and the x minus 2. This one has everything except for the x. So now each of those denominators is going to have 4x, x minus 2, 4x, x minus 2, 4x, x minus 2. And this one winds up being negative 2x plus 4, right, when I distribute this negative across, minus 3x plus 6, because we'll just go ahead and call that a negative 3, and I'm distributing across the x minus 2, plus 3x. All of that over 4x, x minus 2. Well, this cancels with that, and I'm left with negative 2x. Okay, I'm left with negative 2x plus 10. All of that over 4x x minus 2. Okay. Now the original form of the function was x squared, right, over x minus 2. And so, gosh, I probably messed up somewhere around here. Where did I mess up? And here's the derivative, minus 3 over 4. Okay, I probably messed up it just in the simplifying as I'm moving through. Oh well, we'll forget it. But basically this, of course, is getting you back to this right here. Oh, yeah, because this is squared down here. That's where I messed up. Okay, so basically I need another, I need an x squared and an x squared. And I need another x here and here. And basically that winds up being, so negative 2x plus 4, negative 3x squared plus 6x, and then plus 3x squared. All of that over 4x squared x minus 2. There we go. Sorry about that. Boom, boom. I'm left with 4x plus 4 over 4x squared x minus 2. The common factor of 4 obviously cancels, and I'm left x plus 1, x squared x minus 2. So from here down, I've checked both the derivative, and when I changed the form of the derivative, I checked the decomp, and I got exactly back to the integrand, with the exception of that small hiccup. Now, let's go ahead and do one more on this video, and then we shall call this video to a close, and we'll start a second video. Don't want to make them too long for you. Now this one, we need to go ahead and factor the denominator because this one was not given to us in factored form, but you know, you ought to be able to do that. Obviously, remember that the easiest factoring to do and the easiest factoring to forget is that GCF. And once you pull out the GCF, you are left with a quadratic that is really easy to factor. And so I'm left with something like this. Now, if I'm going to do the decomp, we'll pull it over here. That's going to be 3 fractions, since there are 3 unique factors in that denominator, all first-degree linears. And so from here, we're going to multiply through by that common denominator, x minus 3, x plus 1, plus bx, x plus 1, and plus cx, x minus 3. We have 3 factors that can be zeroed out, and so we're going to use the convenient values for those. So let's let x is equal to 0, and that's going to help us get a. So this becomes 7 times 0 plus 3, or 3, and this is a times negative 3 times 1. Now x is equal to 0 is going to make this term 0 and this term 0, so I'm not even going to entertain them. Let x is equal to, let's add x is equal to 3, which will help us isolate b. And so when I plug in 3, I'm going to get 21 plus 3, or 24. And this is going to be b times 3 times 4, because 3 will make the a term and the c term equal to 0. And then let's let x is equal to negative 1, and this is going to be negative 7 plus 3, or negative 4. Negative 1 is going to make the a term and the b term equal to 0, but it's going to leave us with c, negative 1, negative 4. Now this gives me negative 3a is equal to 3, or a is equal to negative 1. This gives me 12b is equal to 24, or b is equal to 2. This leaves me with 4c is equal to negative 4, or c is equal to negative 1. So negative 1, 2, negative 1. So this means that this is negative 1 over x plus 2 over x minus 3 plus negative 1 over x plus 1. And that means that when I set up the integral, it's going to be pretty straightforward. And again, I'll go ahead and put in the step where we actually separate it into separate integrals. It's not necessary, especially at this stage, but every once in a while I kind of like to do it just to see it visually. And we get negative natural log absolute value of x plus 2 natural log absolute value of x minus 3 minus the natural log of x plus 1 plus c. And that, my friends, is your integral. And again, you could check just simply by taking the derivative of this expression right here, and then of course recombining it by doing the common denominator, and it would lead you right back to this original integrand that we have up here. Now, this brings us to the close of video number 1. I hope this has been helpful. If you have any questions, please do shoot me an email, and I will look forward to hearing from you. Bye.